Very pleased to welcome Professor Paul Heslop from Durham University, who's going to give us a summary.
Thank you very much. Thank you for this wonderful conference. It's been fascinating. It's very different to the usual sorts of things that I come along to. Thanks Joanna and everyone for organising it. So I'll get my excuses in early. So I am neither a historian nor a philosopher, and arguably not a physicist. I'm in a maths department. I do work on theoretical physics. It's just depending on your point of view, you might call me a mathematician. So anyway, we'll see how it goes. I was talking to my wife about this and wondering how to start off, and saying it's going to be a very general audience. And she used to be a primary school teacher, and even she thinks I may have gone a bit too wide in the first slide. So anyway, I was thinking, when did we first come across symmetry? And I came across this. So everyone probably did this at some point. You paint half of a butterfly, and then fold it over, and then you get an example of broken symmetry, because it never quite works how it's supposed to. Anyway, so this is obviously x goes to minus x, invariance under that. And then when you're a bit older and you're able to hold a pair of scissors, you might do a snowflake type thing. So here you fold the paper into, well, I could only ever do it in eighths, but in principle you do it in sixths, and cut it, open it out, and you get this symmetric picture. So this is, my e to the I pi over 3 has moved. It should be there. I hope that hasn't happened with all of them. It's probably a PowerPoint issue. Anyway, we can think of it in the complex plane. This is just rotation by 60 degrees, and we can think of this as a function, and the function is invariant if I rotate by 60 degrees. And then obviously if I do 2 rotations, I rotate by 120 degrees, which is also a symmetry, and then you get the idea of a symmetry group. Okay, so these are all examples of symmetry. So more generally, we just say that there's a symmetry in mathematics if you have something, some object, which remains invariant after you do something to it. Okay, so, and then of course the usefulness of symmetries is, well, there are many uses of symmetries, but fundamentally, it just reduces the amount of information that you need to put in. So there's the 2 examples there. I only have to have a sixth of space to do the snowflake thing. Schwarzschild is another nice example that I don't think we've heard about so far. So again, I'm not a historian, but I hear that Einstein said that no one would be able to solve his equations after he came up with them, and Schwarzschild did solve them very quickly afterwards, and he did it, of course, by assuming spherical symmetry and static, so reducing what are 10 nonlinear partial differential equations down to some fairly simple equations, and then solving those. So again, symmetry is very powerful because it just helps in that way. So what about symmetry in physics? So we've heard some talks early this morning about this. I'm glad that we even saw these platonic solids existing. So there's obviously in us, rightly or wrongly, some innate desire to have symmetry. In this case, presumably wrongly. And then we've also seen about these epicycles as well. Here, though, I mean, it's true that orbits are nearly circular, so this is sort of slightly less random than this example here. But obviously, it was taken too far. So maybe there's a cautionary tale here that symmetries are useful, but we, don't necessarily hold on to them too long. And I was interested in what Themis was saying about the similar thing happening with C and CP, right? People thinking that they should be there. I wanted to say a little bit about, just try to clarify in our heads what symmetries we're talking about. So there are symmetries of solutions or of the world. So, for example, translation symmetry. There were some questions about this as well, or rotational symmetry. Like this room isn't rotationally symmetric, although maybe it's slightly, or translation invariant. So usually in fundamental physics, we're talking more about the solutions of equations being symmetric. Although, of course, there's interactions between these things. When you have symmetry breaking, it's the solutions that break the symmetry of the equations themselves, which do still possess the symmetry in question. Okay, so a bit more specifically here. Sorry, everything's all messed up. It's a PowerPoint thing. Anyway, hopefully it still makes sense. So phi, translation invariant, you have a scalar field that transforms. It's a different scalar field. Like the world, if I translated it, looks different. But the point is that when I plug it into a Lagrangian, say, then the Lagrangian is invariant when phi goes to phi prime. The Lagrangian of phi is equal to the Lagrangian of phi prime. You have to do a translation of the phi's to get them in the right place. Okay. So then we heard a little bit about Galileo and about Einstein. So Galileo then went further than translations and rotations, which are sort of fairly apparent. What isn't so apparent necessarily if you're not used to driving in cars and things. That the laws of physics are the same when traveling at a constant speed as well. And then Einstein then modifies this. And I guess the main point here, which I think we've been touching on, is the fact that the symmetry becomes a bit more at the forefront of what's going on. So Lorentz observed this symmetry in Maxwell's equations, and Einstein sort of then put that right at the front of everything. So that the speed of light is constant in all reference frames, and let's have that as the fundamental principle and see what the consequences of those are. Okay, so then we come to the power of symmetry in physics. So, I want to sort of say a bit. This was also touched on it more in a question, I think. That put together with quantum mechanics, special relativity, or Poincare symmetry, becomes like exceptionally powerful. So first of all, it's very difficult to combine them, and it implies that you need quantum field theory. And there's a sort of simple argument for that, because quantum mechanics sort of doesn't allow particles' number to change really, and you need that because of the relation between mass and energy. So you need quantum field theory, and then so every particle then has to be a unitary representation in quantum mechanics. So you need a unitary representation of the Poincare group. And this can be classified. That's then a purely mathematical problem, if you like. And you can classify the representations, and they're classified by spin. And then there's not, you've gradually reduced what physics can look like. So, and then also you can't have higher spins for various reasons, and if you don't want gravity, you have to have spin less than 1. And then there's this concept of the effective field theory, which was touched on in the last talk, which combined with what went before means that at low energies, we kind of are very restricted in what we can write down. So in a Lagrangian, you write down certain terms involving scalars, fermions, and gauge fields. But more than that, the terms you can write down in the Lagrangian, which the Lagrangian, by the way, defines everything. It defines the equations of motion classically, but also at the quantum level via the path integral, it defines your quantum theory. So the Lagrangian you can think of as basically defining the theory, but there's not much you can write down. So again, you've got these particles. The interactions are also seriously constrained if you're looking at low energies. And this is the sort of point of view that Wilson came up with in the 70s. So for example, for scalars, in 4 dimensions, you can write down a kinetic type term or just a single scalar here. Phi squared is a mass term, phi cubed, phi to the 4th, but you can't, you stop there. You can't write down phi to the 5th because it comes with a coupling which then gets renormalized, and below a certain energy, you will no longer see it. So it's pretty restricted. Of course, it still allows for quite a lot of possibilities, and the standard model is one possibility. So spin 0, spin a half, spin 1, and okay, I'm not going to go through these. We've had a really nice talk describing various aspects of this. And there's spontaneous symmetry breaking, but of course it's still constraining. Okay, but the point is it fits within this framework that is sort of theoretically motivated. There's still a lot of choice, but there's a lot of restriction. You can't just do whatever you like. There's only certain interaction terms that you can write down. Good. Now, as well as Poincare symmetry, there are, of course, additional symmetries. So first of all, I can have more than one scalar or more than one fermion. And then they can rotate into each other. So roughly speaking like this. This is like, an SU2 or an SU3 where I is an index. And you can also have local symmetries. So these are symmetries like that, but they depend on space-time. So I indicate that with an X here. Okay, and this is called a local gauge symmetry, and spin 1 particles are inherently connected with this. So your gauge bosons of force are inherently connected with a local gauge symmetry. And similarly, gravity can be thought of as having a local Lorentz symmetry, which essentially just becomes your diffeomorphisms or the coordinate independence of curved space-time. And then there's this sort of buzzword that you hear people saying that gauge symmetry is not actually a symmetry for precisely the reason I've just said. If I'm describing a curved space-time, the fact that I need to put coordinates on it and have a metric to describe it is not an inherent part of the thing itself. Someone else comes along with some other coordinates. They're describing exactly the same physical object, but with different coordinates. And this local symmetry is just the map from one person's point of view to another. And the same is true with gauge symmetry, with the spin 1 local gauge symmetry. So just to say that a bit different, it depends a bit on what space you're acting on. This symmetry of what is the question. So again, and this is all messed up, but what I wanted to say here was that for the snowflake example, mathematically, I can think of a function on C divided by Z6. So I can really think of this as my space, and then I don't have a symmetry anymore. Now, I haven't really done anything here. It's just sort of mathematical degree pokery, if you like, but it's a different point of view. So I'm sort of advocating that gauge symmetry is the same thing. It's maybe not a physical symmetry, but of course it's still useful. It's a mathematical symmetry of the Lagrangian, and it's still highly constraining and highly useful. Okay, but crucially, why people say it's not a symmetry, it doesn't actually act on the Hilbert space, on the actual physical situation. Okay, so I want to now shift gears slightly and talk about what I kind of spend most of my time thinking about. And I'm in a maths department, so I'm allowed to do this. I ask the question, in the space of all quantum field theories, let's try and find the simplest one and try and understand that. Because we have lots of problems just understanding quantum field theory in general. And we kind of need to understand quantum field theory better. Understand here means compute predictions. So the LHC is computing lots of prediction, is actually doing experiments to find the outcomes of certain events. And we need theoretical predictions in order to see whether the events actually agree with the standard model or give us new physics. And you may not know this, but sometimes the theory is actually behind the experiment. We can't actually predict with enough accuracy what is supposed to happen. So we can't tell if there's new physics at LHC or not in certain situations. So anyway, we need to, we need better ways of understanding the quantum field theory, the standard model that we know. And a way to think about that is to try and, first of all, understand a simple model of a quantum field theory. Okay, so it's like that sort of idea where you consider a spherical cow in a vacuum. Okay, so you're obviously... yeah. So a question you can ask is more symmetries. What more symmetries can I have? And there's mathematical theorems out there that tell you what you're allowed to do. You cannot just incorporate Poincare with a bigger symmetry. Poincare symmetry, well, let's look, Lorentz is SO3, 1. Can I think of that as lying in some SO5 or 6, 1 or something? No, you can't. You can't do that. There's a theorem that says if you do that, the S matrix that comes out is trivial. So that there's nothing going on. It's basically a free theory. So what can you do? Well, actually, you can evade this theorem. So this theorem sort of assumes a normal idea of what a group is, a standard idea of a group. So the way to evade it are all various ways of kind of generalizing the concept of a group. So the one that we look at is generalizing a group to a supergroup. So this involves supersymmetry, we just heard about. But here, I'm mainly motivated from a theoretical point of view of looking at a more symmetric quantum field theory. So supersymmetry is a bit like the rotation I had before. It sends a scalar to another scalar. But the only difference now is it can send a scalar to a fermion. So it's a symmetry that rotates particles of different spin. Okay, so you can ask what's the maximal possible supersymmetry that you can have? Okay, which is like the maximal possible symmetry. It's a very easy argument. Maybe I don't have time to go through it, but basically you can do 4 jumps to go from spin or helicity -1 to 1. After that, if you have more than 4 jumps, you inevitably go to spin 3 halves, which then becomes gravity. So if you just want a non-gravitational theory, n equals 4, that's the amount of supersymmetry is the most you can have. Okay, and I just really want to advertise n equals 4 super-Yang-Mills theory. It's got an unfortunately complicated name, but it's an area of a huge amount of research people are working on. Because it's this most symmetric theory. And then it has many additional properties that it needn't have had, on top of the fact that it's the most supersymmetric one. So it's often called the hydrogen atom of quantum field theory, because of this simplicity. A lot of the amplitudes that you compute from it are, well, in some case, they're exactly equal to QCD amplitudes, and even when they're not, they give a kind of a well-defined part of the QCD amplitudes. It's got a sort of completely fixed Lagrangian. It's complicated looking if you write it out. Not as complicated as the standard model, though, but it's completely fixed by the supersymmetry. Up to a single coupling, a single parameter, and the gauge group. It's a gauge theory, so you can put any gauge group you want on it. It's also finite, so there aren't any UV divergences. So it's actually a conformal field theory. And the point of view that I'm sort of advocating to study it is that actually we're learning a lot about this theory, and then some of the techniques that are developed are then used for people who are doing more phenomenologically relevant studies. Okay, and then there's this hope that we have that it would be exactly solvable in 4D, in the way that some theories are in 1+1 dimensions. Okay, well, I probably haven't got too much longer, but here's an example of the sort of thing that happens time and time again in this sort of area of research. So people do calculations, right? So there's a 24-page calculation. Here's a kind of 2 pages of it. So this is just do Feynman diagrams, compute them all, massive calculation. And this is just to compute a 5-point amplitude of gluons. And it was done by Park and Taylor. They also did a 6-point, where there's a 100-page calculation. And both of them, this horrendous expression, well, numerically, they checked that it was equal to this expression. OK, I don't have the time to explain what the things are, but the main point is that it's a very simple expression. And now, as I mentioned, some amplitudes in n equals 4 super young males are the same as QCD amplitudes. This is a QCD calculation. So using that fact, actually n equals 4 supersymmetry gives you this automatically. It's the only thing that you can write down for this particular amplitude. Then there are hidden symmetries. I've been looking at this sort of thing. So there's a relation between the 3 key objects, correlated amplitudes, Wilson loops. As we've been seeing, hidden symmetries appear but are hard to find, but they exist. How do I see if there's a symmetry? If it's like a 2-dimensional object, I can see it, but if it's a mathematical thing, I can't. So yeah, lots of symmetries, but I guess the main point maybe I'll just advocate is, again, these arrows are going from computations to symmetries. There's this sort of symbiotic relationship. You do computations, you observe this complicated thing actually simplifies, then you think, why is it simplifying? What symmetry or structure is there? And after you've got that, then you can do much better computations. The computation you did originally is now almost trivial, and you can go further. And that's happened with all of these cases, which I don't really have time to talk about. Oh, and another thing at n equals 4 super young males is this called amplituhedron, which is that the amplitudes in it can be obtained out of pure geometry. This is really just polygons are an example of an amplituhedron, and then you have higher dimensional versions of polygons. And the amplitudes are equivalent to these. And finally, on my advert for n equals 4 super young males is the ADS-CFT correspondence, which is one of the big developments in the last 25 years, I guess now. So maybe people have heard of this, but it's an amazing duality between a gauge theory, which people want to understand better, and quantum gravity, which we certainly want to understand better. And this is basically saying that they're the same thing. So it's a holographic correspondence. You can think of gauge theory as a definition of quantum gravity. And the point is that the best understood example of this maps n equals 4 super young males to a 2B string theory on ADS5 crystallography. So a certain well-defined string theory and a well-defined n equals 4 super young males. So this is your quantum gravity. This is just a gauge. This is really just a gauge theory. So think of this as QCD, but simpler than QCD. And so nowadays, another development, recent development, is so-called bootstrap in conformal field theories, enabling us to compute things that we wouldn't normally be able to compute. So non-perturbative things, things that when there's strong interactions, we can compute them here and get predictions for things on the quantum gravity side. Okay, good. So, well, I don't have much time left. This is not something I've worked on, but it seems very relevant for this conference, because this is something really over the last few years that has shot up in the in this area of theoretical physics, which are generalized symmetries in quantum field theory. So I was kind of hoping that someone would have done Noether's theorem with equations. No one quite did that, I don't think. But anyway, hopefully people know Noether's theorem, so that you get a current, and it's a conserved current, and then you can produce a conserved charge by taking the zero component and integrating over space. Okay, and d by dt q just comes from plugging d by dt in there and using that, and you get a boundary term. And in the quantum theory, then the exponential of q is the generator of the original symmetry. So now, actually, oh man, it's messed up again, but never mind. This is supposed to be u of depending on md minus 1. And it's equal to the exponential of, so this is the same thing that went before, basically. So j mu I can think of as a 1 form, and d mu j mu equals 0 I can think of as d star j equals 0, and I can integrate this over any manifold. So we're used to, okay, thanks. We're used to thinking of integrating over space, j naught over space, but you can integrate the current over any codimension 1 manifold in space-time, d minus 1 hypersurface. Okay, so this is just ordinary Noether's theorem in quantum field theory. Has this thing. I have topological operators in quantum field theory which interact with local operators to give the symmetry. And the new thing over the last few years is to consider instead higher form currents. So instead of J mu, I have a p plus 1 form current, and I can integrate those over d minus p minus 1 surfaces, and I generate sort of p-form symmetries. And people are studying that. They're finding new, these are generalized symmetries. There can even be things called non-invertible symmetries. So they're symmetries only at the quantum level. They don't come from any symmetry of a Lagrangian or anything. Okay, good. Well, there's the summary of the summary. But just to give you an example, so there's these sorts of papers coming out all the time, and even the standard model has been found to have these non-invertible global symmetries. Okay, thank you.